In our second video dealing with titration, we're going to look at a titration of a weak acid with a strong base. So let's arrow over a couple of pages in our notes, and we see this titration curve here for a weak acid with a strong base. Now notice how this looks. First of all, if you remember the strong acid started out at a really low pH, and we ended up with this almost vertical situation for our endpoint. But with a weak acid, notice how it looks different. We're going to have a little bit higher pH. It's still, of course, going to be acidic. It's still an acid, but it is going to be a little bit higher of a pH than it was for the strong acid. So we're going to recognize that if we have to notice whether it's a weak acid or a strong acid starting us out. And notice something else about the area where we have this endpoint. It's much shorter. And if you'll notice the center of it is going to be above 7. So we're going to have, at that endpoint, we're going to have a pH that's slightly basic. And since it's a strong base, when we end up and we go past the endpoint, we're still going to end up with that high pH for our solution at that point. Now, one of the things that we want to make a note of, and we'll do a lab with this, halfway to the equivalence point, the pH is going to be equal to the pKa of the acid. So if we come up here to this graph, and if the equivalence point is at 25, let's say, then halfway to this, about 12.5, we're going to have a situation where we have the pH and the pKa are going to be the same. So if the pH is about 4.5, then the pKa of that acid is also going to be 4.5. So that's a very interesting point to remember about these weak acids and strong base situations. So keep that in mind. Okay, so an example. We know we're dealing with titration if what they give us is one acid and one base. And our main first goal is to decide whether we're dealing with a weak or strong acids or bases. This particular one is dealing with NaOH, which is a strong base, and HF, which is a weak acid. So right away, we know we're dealing with a titration problem because there's an acid and a base, one of each, nothing else. So as soon as we know we're dealing with a strong and a weak combination, we know that we are going to end up with two parts to this problem. We're going to have a strong part, which is CBAC, and we're going to have a weak part, which is rice. The strong drives the reaction, and it's going to start out the reaction. So for this, remember, for NaOH, since it's a strong base, all we care about is the OH minus. It's going to react with the acid, HF, and it's going to steal a hydrogen. It's a dirty, nasty hydrogen stealer, so we're going to get H2O and F minus left over. So there's our reaction. Very important that we know how this is going to react for our first reaction, for our strong reaction. Now remember, CBAC is in moles. So in both of these cases, at any time we're dealing with CBAC, we have to change all of our concentrations to moles. And I am not going to do this calculation every time because it just wastes time on the video. I'm going to do it on this first one, but from then on, I'm just going to make a note of it and say, well, if you do the calculation, this is what you'll end up with. We've got 0.030 liters, and we've got 0.1 moles per liter. So our initial concentration of our hydroxide ion is going to be 0.003 moles, excuse me. I said concentration, I mean moles. You've got to be in moles for CBAC for the strong part. So we're always going to start the strong first, the weak second. So we've got 0.0030 moles of hydroxide, And for our concentration or for our number of moles of HF, we've got 0.050 liters times 0.10 moles per liter, which is going to give us 0.005 moles of HF. Of course, we don't care about water because it's a liquid. So that's what we get before. We're going to react it. And we've got the least amount of hydroxide, so it's going to completely react. So I really need to write the moles again, 0.0030, and this really should have a 0 here as well. And then over on this other side, be careful, this is plus 0.0030. So after, I'm going to get 0 for my hydroxide, 0.0020 moles of my HF, and 0.003 moles of F minus. Remember, we always change back to molarity for our final step. And since we added together 30 milliliters of the base and 50 milliliters of the acid, we've now got 80 milliliters total, or 0.08 liters. So I'm going to divide both of these by 0.08, and I'm going to do that actually in a different color to show that's a little bit different step. And when I do, I end up with 0.025 molar for my HF and 0.0375 molar for my F minus. So that takes care of the CBAT part. And now for the next part, I'm going to show the rice for the weak. And the weak part of this reaction was our weak acid, so that's the reaction I'm going to show. Very important that you get the reactions right. So the weak acid is the next reaction, so my HF is going to react, and it's weak, so it gets the weak arrow, and it's going to form H plus the F minus. And at the beginning, we just did this. This is what we've got in the solution right now after we reacted the strong base. So we've got 0.025 molar HF, 0.0375 molar F minus, and we've got 0 for our H plus. So our change is going to be minus X plus X plus X. And I end up with, for my equilibrium concentration, 0.025 minus X, X, and 0.0375 plus X. So now I'm ready to write my equilibrium expression. Ka is going to be equal to H plus times F minus over the HF. Ka for this particular acid, it gave it to us up above, is when in doubt, go to the top of the problem, 7.2 times 10 to the minus fourth. And that's going to be equal to our 0.0375, well, X first, times 0. Rewrite that. X for our H plus times the 0.0375 plus X for our F minus, and then on the bottom our 0.025 minus X. Remember, that's approximately equal to X times 0.0375 over 0.025. We can neglect those X's. So multiplying, solving for X, I'm not going to go through the interim values, but what we end up with, and you can calculate this yourself to make sure you're getting the correct answer, 4.8 times 10 to the minus fourth molar. Okay, so what do we have? Molar what? We go back here and it looks like X is our H plus in this case. We have to be very careful that we're paying attention to that. So it wanted pH. pH is the negative log of that value. So our pH is 3.32. So that's our initial, that's our pH value before we reach the endpoint at this point. So remember all of these problems, I'm going to do one before you reach the endpoint, at the endpoint, and after the endpoint. So our next one is going to be at the endpoint. So let's look at how that plays out. We're still going to have the same reaction. OH minus, it's still the strong first. OH minus is going to be reacting with the HF and forming H2O plus F minus. And I told you I wasn't going to work through all these calculations every time. If you do the calculation for OH minus, you get 0.0050 moles. And the same thing for HF. 0 for F minus, and we don't care about water. So these are going to go away. And we're going to subtract on both of these, add 0.0050 on this one. And what we end up with is 0, 0, and 0.0050 for our F minus. Remember, the last part of CBAC is to divide by total liters. There's 100 milliliters total when we add 50 plus 50, which is 0.10 liters. So we end up with a concentration of 0.050 molar F minus. Now, at this point, the HF has been used up. There's no HF in this solution now. The OH minus has been used up. The only thing that's in this solution now is the F minus. So as soon as we reach this situation where all that's left is F minus, it's going to happen every time we get to the endpoint for these weak, strong reactions. That's what our reaction is going to involve, because all that's in there is F minus. And what's water going to do to that weak anion? It's going to attack. And when it does, then that F minus is going to grab hold of one of those hydrogens and leave the OH minus behind. So this is the weak reaction that's going to start. We always look at what's left over, and that's going to start our reaction. So initial for F minus is 0.050 molar. Don't care about water. 0 and 0 for the others. Minus X, plus X, plus X. And we get 0.050 minus X, X, and X. And guys, here is the point where we are going to get ourselves in trouble on these endpoint reactions, because all that's left over is that anion. That anion, which we refer to often as the anion of the salt of that particular weak acid. So when we have this situation, what do we have to do? There's no K for F minus. So in a weak, strong reaction at the endpoint, you have to know that we need a new K for this reaction. So remember, the equation for this is that the new K, which in this case, this is acting like a base since it's a dirty, nasty hydrogen stealer. The new Kb is going to be 1 times 10 to the minus 14th. Remember this? Divided by the Ka, the conjugate pair, okay, the acid. So above we saw that the acid was 7.2 times 10 to the negative fourth. So our new Kb is 1.39 times 10 to the minus 11th. Okay, so that's our new Kb. And now we can set up our equilibrium expression. Kb is going to be equal to HF times OH minus over F minus. We just said that Kb, which is 1.39 times 10 to the minus 11th, is equal to x squared over 0.05 minus x, which remember is approximately equal to x squared over 0.050 when we neglect x. So when we solve for x, trying to write this in different colors to keep it separate, so because I'm running out of room, x is going to be, we've got to solve for x squared and then take the square root. I'm not going to go through that calculation, but x is going to equal 8.33 times 10 to the minus 7th. Now keep in mind that this is molar OH minus. So this is the concentration of the hydroxide. The POH is the negative log of that, so the POH is 6.08. 14 minus that, we've done this a lot of times, I'm not going to write it all up. 14 minus that is going to be 7.92 for our pH of this solution. Okay, so I consider the endpoint to be the most difficult of the problems since we have to find that new K. Got to remember that that's going to happen when those first two substances are exactly used up. Okay, so let's do our final one where we're past the endpoint and see what happens there. We've still got the same situation. The strong is reacting with the weak. It's driving the reaction. We're going to get H2O plus the F minus. And now we have, if you do the calculation, we have 0.0060 moles of OH minus and 0.0050 moles of HF. We don't care, and we're starting out with 0 for our F minus. Now the HF gets used up. So the HF gets used up, and we end up now with excess OH minus. And this is where, and there's no way to do this but to memorize it. This is where you have to know that once we get past the endpoint, the strong is leading the way again. The strong overpowers that weak. Yes, there's some weak base here now, but this strong base completely overpowers it. And when we're past the endpoint, all we're going to look at is the amount of strong OH minus that we have left in the solution. The F minus is just not going to make any difference to the overall pH of this solution. So we're going to simply take this value and change it to molarity by dividing by the total liters, which in this case is going to be it's 110 milliliters, so 0.110 liters. And we get a concentration of 0.00909 molar OH minus. Again, the F minus concentration makes no difference in this calculation of pH. POH then is going to be the negative log of that value. We've done this lots of times. It ends up being 2.04. And when we subtract that value from 14, we get a pH value for this solution of 11.96. So that's this concentration this far past that endpoint.